Hello everyone, in this talk I will present our work DeepLens for interactive out-of-distribution data detection in NLP models. This work was done by my collaborators and me from the University of Alberta and Alberta Machine Intelligence Institute in Canada, as well as Purdue University in the USA. One of the fundamental assumptions in machine learning theory is that the training data and test data should share a similar distribution. However, this is usually hard to be achieved in the real world. The test data can easily have a shifted distribution compared with the training data. Distribution shift and out-of-distribution data could lead to ML models' reliability and trustworthiness issues. For example, in 2013, Google flu trends model failed to predict the flu season, missing the peak of that flu season by 140%. One of the biggest reasons behind such failure is that the Google's model failed to make correct predictions when user search behavior has changed. This is a typical type of data distribution shift. During the continuous delivery of machine learning software, developers want to keep the models reliable when new data comes. Therefore, they need to detect and understand potential distribution shifts and out-of-distribution data. To this end, a few techniques have been proposed to help developers interactively detect and understand OOD data in images. While images are more glanceable for humans, for example, it is easy to tell that these two images are in different data distributions. However, text data are usually more difficult to interpret, which requires significant cognitive efforts when reading long text. Therefore, there is an urgent need to provide support for detecting OOD data for text and NLP models. To address the challenges, we summarize 5 user needs from previous literature about detecting and diagnosing OOD issues in machine learning. First, users should be able to automatically detect OOD data, as the dataset size could be very large. Second, users should be able to understand why a sample is detected as OOD. Third, there could be many different topics hiding in the detected OOD samples. Therefore, users should be able to identify different types of OOD data. Fourth, users wish they could compare OOD data with in-distribution data to contextualize the distribution difference. Finally, users should be able to investigate OOD issues from both global and local perspectives. Based on these user needs, we design an interactive system that separates the process of detecting and diagnosing OOD issues for NLP models into 3 different steps. First is the automatic detection of OOD data. Second is exploring different types of distribution shifts in detected OOD samples through clustering. The last one is to understand a specific OOD instance by comparing it with in-distribution counterpart and using keywords highlighting to speed up the process. We built up DeepLens, an interactive system that supports users in efficiently detecting, exploring, and understanding OOD data in large text corpora. DeepLens has 4 different tightly coordinated views. The first view is a distribution view. In the distribution view, users can drag the slider to adjust the OOD score threshold and inspect the icon array to check if the threshold is good enough to separate in-distribution and out-of-distribution data. Users can also inspect the OOD score's distribution across training and test dataset. The second view is the instance view, which displays in-distribution and out-of-distribution data in 2 separate data grades. In the instance view, users can sort, filter, or even search for keywords in both 2 data grades. The third view is the cluster view. In DeepLens, we leverage the embedding information to cluster the OOD data. This is to help users quickly find potential OOD topics. When users click on a specific cluster region, they can dive into this cluster. When hovering over a node, they can check the OOD score of a specific data point. They can also check the keywords that usually appear with this cluster by inspecting the word cloud. For example, here, This cluster contains a lot of data about sports, as we can see keywords like player, team, and game. The last one is the highlighting view. In the highlighting view, users can compare the ID and OOD data that they selected from the instance view or the cluster view. We use neuron activation analysis to highlight the semantically similar salient words. In this way, users can quickly learn about the topic of a long text without reading it in detail. We can see that this in-distribution data contains words like planet, Earth, and human. All these words are related to fundamental science. However, this OOD data contains words like players, team, and hockey. Therefore, this data instance is very likely about sports. We conducted a within-subject user study with 24 developers to evaluate the effectiveness of DeepLens. We created a baseline for our user study, which is a variant of DeepLens, by disabling the cluster view and highlighting view. We conducted our user study on 4 different NLP tasks, including 2 different types of distribution shift, semantic shift, and background shift. We found that when using DeepLens, participants found more topics of OOD data while making fewer mistakes compared with using the baseline. In all 4 tasks, participants averagely provide more than 3 OOD topics when using DeepLens. At the same time, they provided less than 1 incorrect OOD topic on average. We also found that users were more confident with their findings when using DeepLens. Most of them gave credit to the cluster view when talking about such performance difference. One developer said, "By going through clusters, I can find trends faster than going through individual data points." In the post-task survey, participants specifically highlight the contribution of cluster view and salient words visualization. One participant mentioned that the clustering helped them quickly find 2 different topics. Another participant commented that when verifying their hypothesis about whether a certain instance is OOD, highlighted keywords reduce the time consumption. Finally, 22 out of 24 participants strongly prefer DeepLens over the baseline, and they specifically mention the keywords in the cluster view are the key reasons that they would go with DeepLens. We also found a few design implications through our user study. First, we found that it is equally important to help developers understand and explore different types of OOD data compared with only detecting them. Second, we found that compared with a fully automatic process, users prefer to verify their hypothesis by themselves, and eventually, such an interactive process improved users' performance and confidence. Finally, we found that keywords help users examine OOD data in the context of normal samples. In the cluster view, keywords help users quickly find topics of a set of OOD data from a global perspective. While in the highlighting view, highlighted salient words help users quickly understand the key information of a data instance from a local perspective. To conclude this presentation, in this work, we present an interactive system for detecting, exploring, and understanding out-of-distribution issues in NLP models. Our user study showed that through an interactive process with future support, the developer's efficiency and productivity can be highly improved. Here is a preprint version of our paper, as well as video demos and our source code. Please feel free to reach out if you have any questions. Thank you.